My name is Todd McKinney. I go to the University of Alabama, Huntsville, and I actually also work for NOAA Air Resource Laboratory under the HYSPLIT team. I'm actually an intern for the summer, doing some HYSPLIT analysis using these super pressure balloons. So probably a lot of you already know about pico ballooning and all that stuff. I'm going to give a little brief introduction to that, but we're going to really talk about HYSPLIT stuff because, HYSPLIT is probably one of the most important tools for the balloonist, I definitely believe. I'm also a member of the Space Hardware Club, just like Jaden, who was one of our presenters before. This project is funded by the Space Hardware Club, so I just want to mention that because they've been really kind for throwing funding my way to do these awesome launches. So a little bit of an outline. Like I said, we're going to talk about super pressure balloons, just a little summary. I know we've talked a lot in the Equinox project, and Bill has already talked a lot about the sky trackers and how he gets all the data. So the meat of this is going to be talking about NOAA HYSPLIT, and then we're going to kind of touch a little bit on kind of some other stuff that this project has been working on, such as possible launches in Antarctica with these SBS-13 balloons and possibly venting latex balloons. So let's get into it. All right, so right off the bat, I think we all know super pressure balloons. For this project, we use the SBS-13 from Scientific Balloon Solutions. It is made out of that nice polyethylene film, and we use hydrogen because we want those long duration flights and we want to fly as high as possible. And hydrogen is a bigger molecule, so it's not going to diffuse through the balloon membrane as quicker. And it's cheap. That's a big thing too. So like I said, we usually have a stable float altitude, and of course that is going to change a little bit as we go up and down in latitude depending on the density of the atmosphere, but that allows us to have these really amazing long duration missions. So I put a little altitude versus time curve for one of the flights. All right, so we've actually launched 3. We did this this last winter season. We did 4 balloons with call signs K4UH-4, -6, and -5. -6 is still flying. It's been in the air for 120 days right now. -5 was in the air for I think 110 days, and -4 was in the air for 30 days. So we got a really great sample from all these balloons for using the data for HYSPLIT analysis, and we'll get to that in a second. I always put this slide here because every conversation I have with somebody, there's always like, what if it goes over North Korea? What if they shoot it down? Like stuff like that. So I always say that we're, following all the rules, the FAA 101 exemption rules, which is, our payload mass and all that stuff. We follow all those. And of course, we turn off our trackers over those areas where, they don't want trackers being transmitted. I like to include this photo here because it includes the geofence over North Korea. This is one of the -4 balloons. You can see right after we left that geofence, the sky tracker turned on. It recognized that border. So I think this is a really cool photo. Went through North Korea, but right after we leave, we turn on. So I think that's really cool. All right, so Bill's already really given a good introduction. We've been flying his Whisper Sky Trackers. Honestly, this is probably one of the best tools out there, especially he makes it so simple to fly these balloons. It's, as you can see, really lightweight. Just me holding it right here. And it's solar powered, so as if we're looking at trajectories, we only get tracking during the daytime. And of course, that propagation off the ionosphere using the 20-meter band is amazing. I mean, this is what makes this global trajectory validation so useful to the ARL people up in College Park, Maryland, because radiosondes are, line of sight. So, and they, it's a 2-hour long flight maybe. This is essentially a horizontal sounding, I like to call it. Instead of a vertical sounding, we can actually kind of do like a horizontal sounding on a global level. So it's absolutely amazing, and I have had no problems with these sky trackers. So big props to Bill for helping me out with this project and getting some excellent equipment to do this study. All right, so I also made this custom website This is really cool. I'm a part of the Space Hardware Club, so I really wanted to give back to the club as well. And essentially what this is a place where people can come and comment on where they've seen these balloons, where they're from, their call signs, kind of start a little conversation, a little community. So if you want to go to that website, feel free to comment, say anything you want. We also have a ASH data visualization site, which takes you to the one of the hub maps, where we also do a little reporting on the position. So I really like this idea of, seeing all these people from around the world commenting on where they've seen it in different languages. And, it's just really cool. It makes the world really, really small, and I like it. It's a great experience, especially with these balloons that are traveling, very, very, very far distances. All right, so real quick, before we go into HYSPLIT stuff, this is some raw data from the balloons we've collected. I mean, like I said, we have a massive sample of balloon points. So I've gone ahead and compiled all this data into really interesting, we call them 2D histograms. So you can see for the latitude versus longitude plot between the three balloons. This is all the three balloon data for these histograms. You can see where they like to frequent, which is pretty interesting. And you can also see, that relationship between latitude and float altitude. We're floating lower at higher latitudes and than our lower latitudes. Very nice linear curve. And then we also have some balloon velocities, and I've gone ahead and I've plotted just velocities over time. And you can see these vary a lot. I mean, we get into so many different weather patterns where we're wrapping around low pressure systems or we're scraping down by the equator. So it really will vary a lot. And I'll talk about that a lot when I talk about HYSPLIT. All right, so HYSPLIT. Like I said, I'm working for Air Resource Laboratory up in College Park, Maryland, doing this little balloon study. So I'm just going to talk a little bit about HYSPLIT. If I'm pretty sure everyone has used, a balloon landing predictor, or, even run a HYSPLIT model on the website. All of that it comes down to this amazing predicting software, and it's all kind of based on this HYSPLIT model. So right off the bat, HYSPLIT is an atmospheric transport and dispersion model developed by NOAA, Air Resource Laboratories. So when we talk about a trajectory, we're talking about a simulated movement. So this is a really nice image right here. This is kind of like, if you can think of like a little point, like say a power plant spewing out some pollutant. We're just transporting that pollutant along a grid size. So meteorological data grids are required to run HYSPLIT. We are taking what we are observing in a certain area, could be a 1 degree grid or a ½ degree grid, and we're taking that information and we're adding it to allow that particle to move along. It's mostly wind vectors. So it's a really, really cool way of taking all these observations and pulling into one source to allow us to know where something's going. And NOAA HYSPLIT does so much more than just normal trajectories. They do dispersion. They can model radiative fallout. So if there's a nuclear accident, they can model those particles. They can, like I said, model pollutants or oil spills, oil burns. It's limitless stuff you can do with HYSPLIT. So amazing software. So I just want to do a quick representation of what an output HYSPLIT trajectory would be. So I just did a random run right here, and essentially what you're doing is you're putting in your start position, and that includes your time and date, latitude and longitude, your altitude, and your run time. And then that will output this nice graphic, which also outputs height units. So you can have height in meters, you could do pressure, or you could do theta. You can output those in a different, you can also do above ground level. I like doing above sea level, but it generates this graphic, but you can also get this nice trajectory output file. That's what I call it. And it's just a nice list of all these points. And those points are what we can do to compare those points to our super pressure balloon points to see how well these models predict balloon position. So the trajectory output file is definitely the thing I use the most for this study right now. So here's just a really interesting graph. When I was talking about meteorological grids, here's some lists. There's a few lists of them, and you can see there's a lot of options. There's some that are just for the US, and you can see their grid size is actually pretty small. I mean, we're seeing 3-kilometer grid sizes. I mean, that's really high resolution compared to maybe the GFS, which is, you know, a 0.25 degree grid size, which is way larger. And of course, with that comes a lot more data you need. I mean, just one file for one runtime could be 32 gigabytes for the really high resolution stuff. So for this study and for this presentation, I'm just going to talk about the GFS because, you know, these balloons go everywhere. So they go around the world. So we need a meteorological grid system that can be applied to the globe because we're traveling around the globe. We're doing our circumnavigations. All right, so let's talk about how I'm analyzing these trajectories. It's really important because, you know, it's really fun to go on HabHub and to look at your HYSPLIT run or just kind of visually see where it is. But we want a mathematical way where we can say, oh, did this actually work? And if we're traveling, I don't know, 100 days, I mean, being able to mathematically see how well these models run is important, not just visually looking on the map. So the first thing we're using is something called the absolute horizontal trajectory deviation. And that's the vector difference between the modeled and real trajectory displacement vectors. You can think of this as literally just the distance between your HYSPLIT calculated trajectory and your balloon trajectory. So if you're running your model, it's going to start, your AHTD is going to be 0. You're starting at the same point. That's where you're running the model. So over time, it's expected to deviate a little bit. So like I said, we're at t equals 0, where our AHT is 0. And then what we can do is we're using something called the relative horizontal trajectory deviation, and that's a percentage where all we're doing is we're taking the AHTD and we're dividing it by L, which is our average length of the calculated trajectory and the superpressure balloon track. And what's really good about this is this almost normalizes all our trajectories. So if we have a trajectory and we're comparing a trajectory over the United States to maybe a trajectory over China, we can use this L value and divide it by our AHTD to get this nice normalized value to see how well these trajectories perform under many, many different conditions over many different areas. So the RHTD is really good for that. All right, so let's go into some examples with some actually pulling together the HYSPLIT and then the balloon data together. So we're going to talk about short-term versus long-term analysis. So for our short-term, what we're doing is for this balloon study, when the balloon wakes up, so let's say K4UH-4 wakes up for the day, we have a script that runs a model for just 6 hours. We want to see how well that model is doing right at the spot. We're not giving it time to deviate. We want to see if the wind vectors are correct right at the spot. But for long-term analysis, what we're doing is we're saying, okay, well, how long can this model go before we're completely off? Is there any phenomenon that messes up long-term models? You'll see in a second that the Himalayas really play a big part in how well these models can represent balloon position. All right, so let's give some short-term analysis. And the first case I want to talk about is when we are in low velocity conditions. So let's say our SBS 13 is moving very, very slow. We actually have a lot of uncertainty with our models. So the first case I want to talk about is when our speed is uncertain. So this was an example over Turkey for one of our balloons where we are moving an average velocity of around 65 kilometers per hour. And as you can see, this is our latitude versus longitude plot. You can see that our direction, our wind direction is very certain. We know where we're going, but the velocity is not very uncertain. So you can see our AHTD values, kind of nice linear increase, and our RHTD values are around 40% off. So that's when we're not traveling. The model is not predicting the movement speed correctly. That's the first case. The second case is where our direction is uncertain. Our speed might be good, but we don't know really where it's moving to. So another example is over the North Pacific Ocean, our average velocity was around 87 kilometers per hour, and we had a little our direction was a little uncertain as we are curving around a low pressure cell. So that's another example. And you can see, you know, our AHD values are increasing and they're slowly going down as we get around that curve, and our RHTD values are around 30%, so not really good. And finally, this one is god awful. Is when our wind direction and our speed, we don't know what the heck is going on in that area. We're going the wrong way, and we're going at the wrong speed. So we're left with these really high RHTD values above 100%. Because remember, we're dividing by our AHTD by our L value. So if our L value is less than or below our AHTD value, it's going to be a positive value. So this run was really interesting to see when one of our balloons went through Africa. I mean, that thing was not moving at all, and it was moving the wrong way. So that's our third case. So now let's talk about when the models are good, right? We've been talking about kind of the negatives, and that is when we're in our jets. We have very low uncertainty. We know what's going on. So this is another one over at North Pacific Ocean. This is time we were in a jet. There was a jet over that area, and you can see how well the HYSPLIT model can represent these balloon movement. I mean, we are spot on with only peaking in around 4 kilometers for our AHG value and only 2.2% for our RHTD value. So really good. And of course, this is, you know, we still have a little uncertainty with our WHISPER because we're in that grid square, but this resolution is very good for this model evaluation, and this is really good stuff. And that's you know, we're moving pretty fast, 170 kilometers per hour. We know what's going on in that area. Here's another example of a kind of Nova Scotia area where the model is really good as well. We were moving around 260 kilometers per hour. That is extremely fast. We booked it. And you can see really good value still. We only peak around 4.7% RHTD. So really great. All right, so let's pull all this together. And essentially now what I've done is I've graphed this little short-term analysis for every single balloon trajectory we've collected so far. I think this is about a week old. We still have some old balloon data coming in because the Dash 6 is still up in the air. But you can see that the higher values, so lighter like whites are more higher RHTD, so worse model prediction, and our darker values are more better models. It's spot on. And it can really vary. You can see we have whites around darker areas, and sometimes it's vice versa. So really interesting. You can see down by the equator, you know, it's slower velocities. We don't really know what's going on with the winds down the equator. You can also see, we'll talk about this in a second, the Himalayas, right? We don't know, what really gets us there is we don't know how fast something is moving. We get the direction right, but we don't know the speed because of the interactions with the terrain. And it really varies over the oceans. We got white values over here, and we have white values over here, and we also have some dark values. So it really all depends on our synoptic weather and our pressure systems and what's going on in the area. And I'll give a perfect example of that in a second. And then over here, we have an RHTD versus velocities heat map. So you can see there's this really nice trend between how fast we're moving and how good the model is. So you can see as we get into our slower velocities, our models get worse. So it's a nice little exponential trend going on right there. So this really pulls all together for the short-term analysis. All right, so I actually did this, I think 3 days ago. There was this really strong, high gradient, low pressure system that was just off the coast of Alaska, and I was doing some runs. This is called a GEFS 0.5 analysis. And essentially what we're doing is we're running 32 separate trajectories where we change and we tweak a little bit of each model initialization to see and judge uncertainty in the atmosphere. So the black with the dots is our K4UH-6 points. And then we have our average, which is an average of all our different variable changes. And then we have our control, which is just the raw GEFS where we just initialize it and change. We don't change anything of the control. So it's the original run with no changes. And you can see after about 42 hours, we get this massive change in AHTD. So right after we leave a low pressure system, it's when we have this really, really large uncertainty and we don't know what is going on, essentially. So I've actually calculated all the velocities for these models, and you can see we have our nice flow separation around 42 hours. So we're all the models kind of agree up until that point when we're leaving that low pressure system, and then we don't know what's going on. We have these massive spreading of all these velocities. So if you're launching one of these Pico balloons and you see a low pressure system, just know once you go in, you might know what's going on, but once you leave it, you might be where you would never have thought of, because these low pressure systems are very, very hard to forecast in their changes. So this is a really good example, and it really shows how these synoptic changes in weather can affect where our balloons go. All right, so what I mentioned before, I call this the Himalayan corridor. Essentially, just the Himalayas. And what I have done, and what we're really looking at, is how the Himalayas affect these tracer or their balloon movements. So I have two examples. I have one where one of our balloons went through that area, so around the Himalayas, and we have one that dodged it and went through India instead. And we're looking at long-term models and seeing how well the models align with the balloon. So we can see when we go through it, you can see that the velocities are almost offset. We don't know the velocity going into the corridor, right? It's different. We can't predict it. We don't have enough data to predict what's going on. So the HYSPLIT model might take meteorological data in, but that meteorological data is not really what's going on, right? We don't have enough to know. So we get a lot of really offset velocity values from the model in the observed balloon values. We have really high RHTD spikes because what happens is the balloon either gets too far ahead of the model prediction or it staggers behind the model prediction. So sometimes what will happen if you're flying an APRS tracker and you're going over Beijing, you'll like, oh, I'm running a model and it says it should get over here around this time, and you might find it actually is ahead of it or behind it. It usually is kind of never spot on. That's because of this corridor and this interaction between terrain. It's very, very detrimental for long-term trajectories. But then if we have a balloon that dodged it, went through India, I mean, this was probably one of the best long-term models I've ever run. We went through Africa. We went all the way through India. These models were absolutely brilliant. We only got a little bit off towards the end when we went through these slow equatorial regions. But compared to this, where we're literally a continent off, I would say this is amazing, where we can predict a balloon movement almost all the way around the globe. It's absolutely incredible. HYSPLIT is an amazing tool for that. But a continent off, it's all about the data we feed into it. So if I had to summarize the field of meteorology, we just need more data. That's all it is. We need more data to know how to forecast longer and to know what actually is going on in the atmosphere. All right, so for more information on HYSPLIT, I put the website on there. The HYSPLIT team over at Ariel is probably the most amazing group of people. I've been doing balloon stuff since, gosh, maybe 2017. And when I finally started getting into Pico ballooning, I literally sent them a message. I said, hey, I've used HYSPLIT a lot, and what do you think of this balloon project? And they loved it. So they hired me to do some stuff and look at some trajectories. I think my background in amateur radio and atmospheric science has definitely helped, but it's the ARL team is just the best group of people. So if anyone has any questions about HYSPLIT and using it for balloon projects, just shoot me an email. HYSPLIT is great. You can actually open up and do a lot of scripting. You can do your own little runs and own little projects. It's all set up to be community interactive, so it's a great thing. So I've just gone ahead and put the Ready website, we call it. where you can actually compute online trajectories. If you were done a Pico balloon project, you've probably gone to the Ready website and ran a trajectory, but you can also download HYSPLIT and actually run it on your PC. But I would definitely recommend you have some extra space, because when you're downloading all these grid files, let's say you're downloading the GFS, I mean, you're downloading every single grid point on the globe, so you need a lot of space to run those. So that's what's so good about the Ready website. You're running models on their server, so you can look and run models using their resources, and you don't need to download all that stuff. So they set that up to be really community friendly. Other resources, I kind of mentioned this a little bit ago in the conference. I use this all the time, and if you know what a SKUT is, this is an amazing tool to understand what's going, especially for these Pico balloon projects. I can actually, I think I have it pulled up. Essentially, what you can do is you can literally look at any sounding station around the world and see what the conditions are where your Pico balloon is flying. So for instance, the -6 balloon is currently over here. Oh, it actually just updated 17 minutes ago, just woke up. So let's say I want to know kind of what's going on over here. I like to go down here and look for the closest sounding station. And I can actually look at and see what, look what altitude it's flying at and know kind of the conditions. I like to look for moisture. Is there a lot of moisture? Is there a cloud layer there to know if we're in safe conditions? So it's a really great tool. All it is if anyone's used Windy before, you usually come to this and then you go to this little menu over here. You can install a plugin, and then you come down here to Radioson, and you click open, and you can view any balloon flight, and there's also these research boats that do soundings. Antarctica launches soundings. You can change how new the sounding is. And you can also download the soundings as a CSV or a JSON. You can look at the station details, and you can actually view models, what the predicted model sounding is. So it's a really, really great tool. I use it all the time. I definitely recommend that. Let me go back to here. All right, so summary. We successfully deployed these super pressure balloons and made multiple circumnavigations. That is an accomplishment itself. I mean, absolutely incredible to be able to say we did that. We made connections with hundreds of different people around the globe. We found that Bill Brown sky trackers and these SPS 13s are amazing tools. I honestly believe this is going to be the future of meteorology. These little tiny trackers that you can track anywhere, and you really can know what's going on in the area. When I did the math, I've shown that RHTD and the RHTD values are dependent on a lot of different factors, and the Himalayas. If we really want to get our long-term trajectories better, we have to know what's going on in that area. And that includes maybe launching more weather balloons there or deploying more surface stations and stuff. So a little bit looking to the future. I've been in contact with the PI of Niemeyer Station. He does all the meteorological instruments. We just submitted a proposal to fly some SPS 13 Whisper trackers down in Antarctica. This is Rainer. This is one of the guys I talked to who runs the Whisper station down in Niemeyer Station. This is him next to one of the antennas. So he's really excited about these 20-meter trackers and launching these balloons. So hopefully the proposal's accepted and we can send a few down there. It'd be incredible to launch some trackers during the Antarctic summer, where we'll have full transmissions. But then when the sun goes down, we won't have that solar. So. And then looking to the future, we're actually doing some really fun experiments. We're going to do a little experiment tomorrow at the next launch. We're working on a device to vent latex balloons. So we made this little prototype. It's a little vent you stick in your balloon neck, and you have a loose string that's a certain length. And as your balloon expands, the string gets more and more tight until it reaches a certain radius, and it pulls the stopper up, and all the gas vents out to equilibrium. So it's a really cool project, but we're still trying to get the vent seal and working on that. We've actually done 2 test flights. This is kind of funny. The first one, this is the blue one, our spring was too tight on our device, so we actually went up, we vented gas, And then we came back down at the same rate we went up back up. So that was kind of funny. Next flight, we made the spring more loose. We launched at sunset. We came up, we vented, and then we stayed at the stable altitude for around 15 minutes, and then we came down at a velocity around 0.8 meters per second. We think because we launched at sunset and the decreasing temperatures and the sinking air might have caused a little bit of a premature descent, and always improving that seal. It's really important to improve the seal between your vent and your balloon. So we're still working on that, and tomorrow we're going to do something interesting. We're going to drape a lightweight sheet over a latex balloon and tie it. So once it reaches a certain altitude, it might behave like a super pressure balloon. So we're going to test that and see how it goes. That'll be interesting to see if just a normal bed sheet can hold a latex balloon, and if it does, how long can it fly? So that might be a fun little experiment to do tomorrow. All right, so now that we're at the end, I just want to thank you all for listening to me. Does anybody have any questions or any concerns about the project or any question about HYSPLIT? All right.
Hi, this is Mike from Pella, Iowa. This is really more of an anecdotal, highly scientific sixth grader project that we did on one of our around the world PICO flights. I split the class into 4 groups. One group tried to predict the next day or 2 days out using HYSPLIT for the prediction. The other group just kind of eyeballed where it'd been, where it's going, how fast it's going, and they just kind of eyeballed it themselves with no predictive tools at all other than what's inside their brain. The third group used windy.com and tried to put a little bit of visual science to where they think it might go based on upper wind information that they got from Windy. The fourth group, this is the highly scientific part, the fourth group used a random number generator and just picked one of the 3 as their results. And the funny thing about it is the random number group came up to being able, if you just summed up the distance, just the linear distance between the prediction and the actual over the course of, I don't know, about 90 days, I guess. The random number generator group came up with the best predictions overall.
Wow.
So there you go.
So what you're saying is meteorology is just random, right?
I think I'm saying the same thing you're saying, is that we need more information and more data and more predictive tool power to really understand what's going on.
Yeah.
Hey,
yeah,
Todd,
for sure. Yeah, what's up?
I noticed that Himalayan effect years ago using HYSPLIT. I was expecting my payload to arrive in Beijing, China on a certain date and time, and it had been so accurate before that as it was coming across to Africa, and then it came up through the Middle East, and then it was a day late.
Exactly, yep. Every time.
It was right on, spot on where I expected it, but it was almost a whole day late.
Yep. It's all about the interactions between the moving jet and the friction on the surface. We just don't know what's going on there. It's really interesting. So I'm glad you noticed that, Bill. And I'm not going crazy.
Well, I'm glad you confirmed it. I thought I was going crazy. I thought I'd done something wrong in the prediction.
Yeah, no, it's a real thing going on there. So, yeah. Anyone else have any questions?
Well, I was just going to make a comment to Bill. It's been a long time since we developed that tracking program back in the early 2000s, huh, Bill?
Oh, yeah. Well, I first wrote it in 1989.
Yeah. And then we made mapping out of it and everything else in the mid 2000s. And all using that HYSPLIT. So
my first one was called Ball Track, then it was called Balloon Track, and then we did it online Balloon Track. and then it just kind of faded out, and then the UK predict model has taken over. But we did it. I had it written in GW Basic back in the good old days.
And then Troy rewrote it in Perl.
Right.
And then I put it on the maps. So, well, that was a fun project back then. So what you're doing there, Todd, is just awesome to me.
Yeah, and it's really interesting. If y'all heard about I think it was a few months ago, they were trying to do the balloon satellite or internet in Africa, or they were trying to provide internet to some rural communities. And that group actually came to HYSPLIT and they said, hey, like, tell us about HYSPLIT. They gave them the information and then they just left. So those people, those long duration balloons, they are actively sending meteorological file data to the balloons, and it knows what path to go on if it wants to change direction. So it's like, oh, I want to stay in this area. Let me go down to, 4 kilometers to stay in this little zone over here. So
that's one of the things we always talked about being able to do, is send instructions back to the balloon about what's going to happen to change the predicted landing spot. This was before the high pressure balloons, when we were doing everything with latex. And we could always get it within about, I don't know, 10 square miles where it was going to land. But we wanted to be able to narrow that down quite a bit, but we didn't know what was happening to the winds during the flight. So, and when we figured out a way to send it back to them, and then we could predict where it was going to land. But we never got that far. It sort of fell apart before.
87 LMO, Mike out of Arizona, he wrote an APRS tracker that sampled the wind speed, wind direction as the balloon rose.
That's right.
After it burst, he would send down the balloon's position as like KD7 LMO-11, and then he would send down the predicted with a big red X based on the real-time sample on the way up. And so that X would move around as it started figuring out what the descent rate was, which, and if you just follow that red X, and it would be a little different extension number, it'd be like -12, and you just follow the X and it would land right in front of you.
Yep.
And HabHub does that now on the fly. So if you look on tracker.habhub.org during a flight, particularly when it's on its way down, you'll see the predicted landing spot move around. And that's very useful.
It's so nice. And Todd, I wanted to say one more thing. If you need any help going to the South Pole to do something, let me know. I've been wanting to go there for decades already.
All right. Yeah. I've already I've talked to so many people at Niemeyer Station. They are the nicest people. And I don't know, it might happen. And they've actually offered to just say, hey, if you don't want to spend all this money to get someone down there, send them to us. We love this idea. So, they might be deploying them for us. So it's a really big, meteorologists it's just a big community. It's such a great field to be in. Because we're all studying, kind of the same exact one thing, the atmosphere, and we all share it. So that's really interesting.
They have a great whisper station there too. In fact, we sometimes follow their supply boat as it's approaching Antarctica, bringing supplies to them. You can actually work the boat.
Oh yeah, and they're actually that Polarstein boat. The guy was telling me they are moving that up to the North Pole to study propagation up in the north. They found some really interesting results for what frequencies propagate depending on seasons. So they're actually sending the boat up just to study that using Whisper. So you might see the Polarstein up there on Whisper.net. That's what it's doing. It's doing propagative studies up there. So it's really
can
cool.
we send them an APRS receiver and an iGate? Because we've got several APRS balloons circling the Arctic right now. That would be very handy.
Maybe. We'll see. Maybe
just a little Raspberry Pi that would be neat.
Yeah.
Do you know Nathaniel Frizzle?
No, I do not.
Call sign N2, W2 NAF. He's probably more of a space weather person than that, but he's a friend of mine that went there a few years ago up to the North Pole and got to launch some balloons up there and all that. So I was very jealous.
Yeah.
Todd, if you go, you got to join the 300 Club.
Yeah.
Are you familiar with that?
I think you told me about that, Bill, but I probably forgot.
Yeah, when it gets down to minus 100, you have to sit in the sauna bath at 200
Oh,
and then run around the South Pole.
Like, don't you get like a jacket or a shirt or something?
You get a jacket for 300.
Yeah. Yeah, I want that jacket. If you survive, yeah.
Which compensates for the severe frostbite.
Oh yeah. All right. Well, that's all I got. Does anyone else have any questions or comments?
On the last page of online HYSPLIT, there's a couple options for the wind model. I mean can you go over the last page of the online HYSPLIT?
Yeah, you're talking about
isobaric, and
yeah.
There's ISO.
Yeah, that map. Yeah, I know what you're talking about.
And also mention which wind model they should select. I believe.
Oh yeah. So if you're running a model on the Ready website, always go isobaric mode. Especially for super pressure balloons, they float on a surface of constant density. So you want to select that isobaric mode, which usually over shorter periods, even for longer periods, the HYSPLIT model will always keep it at the same pressure level. Sometimes it's a little off, especially when you get more up to more polar areas. There's more dipping and diving with the polar vortex that changes your isobaric preferences. But generally speaking, it's really good of staying on the same iso density as your balloon. So always click isobaric mode for the best results. That's what you want to do.
And the wind model should be GFS.
It depends if you want. If you're in the United States, go ahead and use the most highest quality model, because one of them is like a 2-kilometer resolution. I mean, that's incredible if you really think about it, compared to a 1 degree grid square on the globe. So if you're launching from the West Coast, go ahead and run your higher quality models. You'll get better results over the United States. Of course, once it leaves the United States, you want to switch to the Global Forecast System (GFS) because there's no.
Have you done any analysis between the higher res U.S. models and the global GFS over the United States?
I have, but it's very preliminary right now. And the call sign you gave me for the balloon, I'm probably going to be using that one for the next study to look at that, because these SBS 13s usually book it across the U.S. So usually only get like 2 or 3 days. But when you have one that's just chilling around in the CONUS area, we call it, continental United States, then it's a good test case. So I've started to look at that one balloon you recommended to me, Bill.
Yeah, it's W7PXL-2. I don't know whether it survived the storms in Texas today. I'll have to take a look.
All right. Well, thank you all for letting me talk, and I'm excited for next presentation and for the launches tomorrow. It's going to be a really fun event.